Welcome to another video. Today we're going to be covering the subsurfaces have measure 0, the first lemma. In the future we're going to cover the subsurfaces have measure 0 theorem, but for that we need two lemmas. This is the first of two prep videos for that big theorem. Now, what is the claim? The claim is actually interesting of its own right. Given some charts phi and psi, phi inverse composed with psi is smooth where, now we shall specify the dimensions are a bit off, where phi maps some U subset of the k-dimensional real space and maps it into the n-dimensional real space, and psi, which maps some V, which is a subset of the L-dimensional real space, and maps it into the n-dimensional real space. Now, proof. Now, we let pi be some projection from the n-dimensional real space into W, which is a subset of the k-dimensional real space, where W satisfies that pi composed with the Jacobian of phi of U is equal to W. Right. This implies then that G, if we put it equal to pi after phi, is a diffeomorphism. In particular, it is smooth, and also important on some neighborhood. In some neighborhood U, well, in U. Now, why is it true? Well, we are using the local diffeomorphism theorem here, coupled with the fact that pi is an incredibly beautiful map, right? We begin actually with we know by the local diffeomorphism theorem that phi is some neighborhood in U, call it neighborhood N, is diffeomorphic with some other set in the n-dimensional real space, call it, say, M. And if we couple it with pi, since it will project this m-dimensional real space with which we have an isomorphic relation back into the k-dimensional real space, nothing can go wrong, right? In pictures, it would look something like this. So we would have our pi, which is in the n-dimensional real space, so dimension n. It is isomorphic with some, k, and here we have n-dimensional real space, and then we have the projection pi, which brings it back to the k-dimensional real space. All right. Again, we know it is a diffeomorphism because there is isomorphism between these two sets, right? And so there's also an isomorphism between this set and this set, but then even if we couple these two, it will be also also an isomorphism, because it's precisely what would reversing this relation be, right? We know that the bijection works both ways here by definition of a bijection, and therefore it will work even if we add this other ball here. So, my favorite proof by picture. Now, alright, it's all nice and dandy, but what next? Now, using some simple algebra, we learn that from this, that phi is equal to pi inverse coupled with, well, composed with G, and then that phi inverse. I mean, this may be sort of an illegal move because it is kind of difficult to say what an inverse of projection would be, but we are not interested in this step. We could skip it. It just sort of explanatory, because what we want to obtain is this, that phi inverse is equal to G inverse composed with pi, and this is alright because both G and phi are invertible. Right. But then phi inverse composed with psi is equal to G inverse composed with pi composed with psi. And since we have a composition of a smooth functions on some neighborhood, again, we are invoking the local diffeomorphism theorem. So it is a diffeomorphism on some neighborhood. And that's precisely what we wanted. So this is a diffeomorphism on some neighborhood, and thus it is smooth. And this concludes this short lemma.